All right. So you guys are going to try and prove if this is continuous. So you're going to find the limit from the left of what? Which number? Limit from the left of what number? 3. And then the limit of the right from? 3. And if those are the same, we're going to look for f of 3. And if they're all the same, then it's left, hits the point, carries on, right? So try that out. So we have to do the limit as x approaches 3 from the left. Which function are we using, top, middle, or bottom? Top. So we get x squared minus 9 over x minus 3. If I plug 3 in and I have problems, that means I can't. I have to do something first. I get x plus 3, x minus 3 in the numerator. It's the difference of squares. X minus 3 in the denominator. Okay, guys. The x minus 3's cancel, and then I can plug in. I should have had limit. Ooh, this is bad. I'm undoing this. This is annoying. This is bad. Bad news bears. There we go. I need to have the limit, and make sure you do as well. Check your work. You have the limit as x approaches 3 from the left, and then you have x plus 3, x minus 3 over x minus 3. And then I can plug it in. I get 3 plus 3, which is 6. Perfect. Then I do it from the right. Which equation am I going to use? Top, middle, or bottom?
Bottom.
Why?
It's from the right.
It's from the right. It's greater than 3.
Hi, podcast.
So we get x squared minus 9. 3 squared minus 9, which is 0. So the limit as x approaches 3 of f of x, because it says f of x in the equation, does not exist. Therefore,
Not continuous.
the graph is not continuous.
So would you say not continuous? It's 3.
Sure. Okay, guys. They're talking. You guys are not talking.
Oh, yeah.
They're talking about mathematics. When's the last time you guys tried that? Uh-huh.
Do you have to do therefore one for the DNA still?
No, we have a theory.
Therefore, the graph is not continuous at what?
X equals 3.
X equals 3. Now, guys, if I wanted you to justify it, you would have to say from the left, the graph is approaching 6. From the right, the graph is approaching 0. And therefore, there's a gap in between them, right? Now, if I went to draw this graph at that 6 and that 0, would it be an open dot or a closed dot? Open or closed? It would be open. Why?
Not equal to.
Not equal to, and I would have a closed dot at what coordinate?
9. 3, 9.
3, 9. Because this is the line, this is the equation y equals 9. However, it only exists at 3. So an equation of y equals 9 that only exists at 3 is a coordinate. So this has a coordinate at 3, 9. So this graph from the left is technically approaching 6. Whatever, that's really, we're zoomed in. We're pretending we're very zoomed in. This graph is approaching 6 from the left, and then it's approaching very zoomed in, approaching 0, right? From the right. And then what's the point at? 3, 9, correct? This is a very zoomed in graph, like as if I'm looking very close to 3. Like this is 3, and then over here is like 4, and over here is like 2, right? Like I'm very zoomed in. So I'm approaching
That's like definitely a number out of
6, 0.
It's very accurate.
That's all we need, like on the diploma.
So if you draw a graph like that anywhere else, you know from me being crazy about graphs, that ain't gonna work. Okay? I need very, 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 very accurate graphs on an exam.
It's like you're playing.
I did these guys. Right?
You did.
Oh!
Can you show us how to sing?
This.
Oh, more fun.
A theorem we have here is a polynomial function is continuous on its domain, all real numbers. We know that. Every polynomial function is continuous on its domain, right? There's no breaks in polynomials. X squared, like quadratics, cubics, quartics, quintics, we talked about all those. A rational function is continuous on its domain. Remember vertical asymptotes and the x value of the point of discontinuity. So it's continuous on its domain minus asymptotes, vertical asymptotes, and points of discontinuity, correct? So rational is everywhere else, minus those places. If a function is continuous on an interval, its graph has no holes or gaps on the interval. If a function is continuous on its domain, it will be continuous at every number in its domain. It will be continuous at every number in its domain. Its graph may have holes or gaps at numbers that are not in the domain. So the reason why I can say a rational function is continuous on its domain is it's continuous everywhere but where it can't be, which is your x values in the denominator, your non-permissible values. All right. Oh, there it is. I don't know. There's a random blank page in there, but cool. We're at the intermediate value theorem. So, this is what the theorem says. Let f be a function that is continuous on a closed interval a, b, and f of a can't equal f of b. If n is a number between f of a and f of b, then there is at least a number c in the open interval a, b for which c equals n. Aren't theorems wonderful? Aren't theorems wonderful? All right. Want to know layman's terms of this? If I plug in an f of a and I get a value, and I plug in an f of b and I get a value, there exists a value if the graph is continuous between those values. So for example, if f of a was 3 and f of b was 6, and the graph is continuous, there exists all the values of y between 3 and 6. That's all it's saying.
Why would it say it like that? Like that's like
Because that's an example, and they want to give you a theorem that works for all examples, not just one example. It's like verifying a trig proof. You verified it works for one, but you didn't prove it works for everything because you put in a value. So theorems exist in a way that it works for every single thing. So, for example, if I did this graph that's on our page, f takes on every value between f of a and f of b. So if f of a was here and f of b was here, and I know the graph is continuous, that's the key thing, the graph has to be continuous between those values, then I know every y value exists somewhere in there. The graph could curve like this, or it could do like a straight mad dash and go straight to it, correct? But either way, there will be at least one y value that exists between those two y values. That's all the intermediate values do. Okay? Now this one says a discontinuity at C results in no number at C between A and B. So the graph has to be continuous the whole domain. If the graph is not continuous at the whole domain, for example, if they said the graph is not continuous at C, then I know there exists a value of every y between A and B, but not at C, right? Because there would be that gap there. All right. So this is what's often asked of us with the intermediate value theorem. So it says here, use the intermediate value theorem to show that f of x cubed plus x squared minus x minus 2 has a 0 between 1 and 2. A 0 between 1 and 2. What is a 0? How do I know for a fact that I'm going to get a 0? What do I have to have? I need like f of a to be, or f of a to be either below or above 0, and then f of b has to be the opposite. Because if that's the case, and this graph is continuous. Now, most people don't do the intermediate value theorem wrong. They don't state it correctly at the end to make them actually get full marks. There's the issue. Intermediate value theorem, you have to not only show that there's a value below for one of them and a value above for the other, but you also have to state that the graph, the original graph is continuous between those values. Because if you just say, oh, it's below and it's above, then it exists. No, you have to state there's a continuity in that polynomial between 1 and 2 as well. Or else it doesn't work. So we show one's above, one's below, but we also have to state there's a continuity that because it's a cubic function, it's continuous between 1 and 2, and therefore you would end up having a 0. Okay? So we have to first find our endpoints. So we find f of 1. And we get 1 cubed plus 1 squared minus 1 minus 2, and that gets us negative 1. Then I fill in f of 2. Guys, I'm over it. 2 cubed plus 2 squared minus 2 minus 2 equals what? 8. So people will say, therefore, there's a 0. You can't say that. A 0 means that there's an x-intercept, yes? And just because I have a y below and a y above, if I have a y at -1 and a y at 8, and I just say, now there's a 0, is that true? Could I have just a coordinate at -1 and a coordinate at 8 and it not be continuous? Could I have a gap in between if it wasn't continuous? So not only do I have to state the endpoints, I also have to state that that this f of x is continuous. So since f of x is a cubic function, or you can say a polynomial, it doesn't matter, cubic function, the function will be continuous between the values of x equals 1 and 2, since f of 1 equals -1 and f of 2 equals 8, there exists a 0 between those values. You could, I like personally first listing that since f of 1 is -1, which is below the x-axis, and f of 2 is 8, which is above the x-axis, and this is a cubic function, which is continuous, there will be a 0. I like personally stating the f's first, then saying the function is continuous, and then saying that there exists a 0 because I'm below the x-axis and above, and it crosses. It doesn't matter how you state it, but it does matter that you have to state endpoints. You have to find the endpoints, state the endpoints. You have to find the whatever graph it is, if it's a polynomial or rational, whatever it is, you have to state that it's continuous everywhere for polynomials, therefore it's continuous between 1 and 2, or a rational, you could say it's continuous between 1 and 2, this graph is continuous there, therefore it must cross through, right? But you have to find endpoints, state continuity, then say because of that it would pass through. Now sometimes they don't say is there a 0, sometimes they say is there a value of 7. Well, then you have to show that their endpoint gets you above 7, another endpoint gets you below 7, and therefore, because the graph's continuous, it has to hit 7 at some point, right? So it doesn't have to just be a 0, it could be other values. Either way, there you go.